All right, so in this episode, we're going to be talking about the Lua virtual machine, focusing on the stack and instructions. So, looking at Rerubi source code, we can see that there is an OP mode and OP code table. Well, what is all this? Well, you'll notice that these two tables, it's kind of hard to tell, but they have the same number of elements. And this is because they both store data about Lua instructions. So, a Lua instruction is pretty much just an unsigned number. It represents an object that has arguments, which are also just numbers. There's a couple 8 bits and a larger number and an assigned one. And so you can see OP mode, it can either be kind of use A, B, C, or just A, B, just A, or A and BX, or A and SBX, right? So it can use each instruction can use different arguments. And arguments are just numbers. They're just used in certain ways depending on their mode, right? So this is the OP mode table, and it describes how each B and C arguments are used. So, and here we have this enum. This is the Lua source code. We have OP arg n, which means the argument is not used. U, which means it is used. R, which means it is a register or a jump offset. K, which is a constant or a register / constant. So the only one that you really need to worry about is K, where it can be a constant or a register / constant. So we already talked about constants a little in previous videos, but what are registers? Well, to explain what a register is, we first have to talk about the stack. Essentially, the stack is just a list of Lua values like number, string, table, function, etc. And all instructions do is manipulate the stack, like putting things onto it and using or taking things from it. So, for example, the load K instruction, or the load K instruction takes a target register and puts a target constant into said register, right? So, all that means is that the stack item at index A, which is load K's target register argument, so for example, 0, so stack of 0, will contain the value of whatever the constant is. So when we have the code local foo equals bar, it compiles to load K, R0, K0. R0 being the 0th stack item, and K0 being the constant at index 0. I should tell you that every proto has a list of constants. In this case, the string bar gets added to the main's constant list and sits at index 0, which is how we can get the string bar from just the number 0. So when it says register / constant, when it says register / constant or RK, it means that it can either be an index into the stack, which is called a register, or an index into that constant table. And you should note that Rerubi treats all constant modes as RK. So each OP RK is treated as RK, which is, again, constant or register, since it is always obvious whether it's a register or a constant. So you can see that it checks if the mode is constant, and then it checks if the actual argument itself is a constant. If it is less than or equal to 255, then that means it is a register, because the stack can only hold 255 values. So then it just gets it from the constant list. So let's talk a little bit about individual OP codes. OP codes just represent what an instruction is supposed to do. So an instruction is an object which has an OP code and then arguments. OP code is which type of operation you're going to be doing, like move, locate, load bool. Okay, so since Rerubi is in Lua, it is easy to understand what most OP codes do. For move, we set stack of A to stack of B. For load K, we set stack of A to the constant at index B. For load nil, we set stack items from A to B to nil. For get global, we set stack of A to the constant at index B, indexed into the function environment, and the opposite for set global. For add, we set stack of A to B plus C, and B or C can both be either constants or registers. And the same thing for all the other binary operations. For unary minus, we set stack of A to stack of B negated. For not, we set stack of A to not stack of B. For len, we set stack of A to the length of stack of B, and so on and so on. Let's talk about how the VM loop function works. In a nutshell, all it does is go through a proto's list of instructions and execute them one by one. So first, we have the instruction pointer, also known as PC, meaning program counter. This refers to the current instructions index in the proto's instruction list, and is used for instructions like jump, which allow the program to jump around or start executing in different places. Then we have enum, which represents which OP code the current instruction is. You see it down here and all the checks for move, load k, load bool, load nil, etc. Finally, there's inst, which is just the instruction. So an object containing arguments as well as the OP code. Essentially, this function loops through each instruction. You see that increases the program counter and performs a certain task based on its OP code and its arguments. And you can see, like in jump, all it does is it increases the instruction pointer by a certain number. So for example, we have the code print42. It compiles to get global R0, K0, load K, R1, K1, call R0, 1, 0, return R0, 0. So Rerubi will go instruction by instruction and execute the right task. We first put the global at constant index 0 into register 0. Then we put the constant index 1 into the R1 register, so register 0 or register 1. And then we call the function at register 0 with one argument and no results. The argument being one after the function, so it would be in this case R1, which is 42. Then we return 0 values starting at R0. So that is an overview about how the Lua virtual machine works. Each function contains a list of instructions, and the virtual machine just goes through one by one and executes them using their arguments, which are just numbers that might index into a constant table or potentially even the environment for get global. This is essentially how obfuscators like Ironbrew achieve code execution through what looks like a bunch of random stuff, right? Ironbrew will output a script that is a modified version of Rerubi that will literally just go through a list of encoded instructions and execute them. That is how virtual machine VM obfuscation works.